All right. Hello, class. Mr. P and Hazel here. How you doing, Hazel? She's very tired. Let me see. I pull her this way. Yeah, there you go. What'll do? Um. So, what was I gonna say? One thing I wanted to say is that there will be no lesson tomorrow. Hey, Spicy Pepper, where's Bug? Um, Bug does not like to stay in one place. So I have tried to put him back there, but he just jumps off. Let me see if I can get him to come over here. Bug. Bug, will you come here? Come here, boy. He doesn't want to move. All right. So, yeah. So there's going to be no lesson tomorrow. I'm giving you the day off. And then after that, my plan is to kind of do, even though you guys aren't taking an exam this year, I'm still going to do a little review, and I'll probably give you some kind of short, practice IB exam that'll be sort of like a test for you guys, just to put it all together. Because some of you are taking the HL exam next year. And also, I just think taking a summative test is a good way to kind of like put all your knowledge together. Okay. Let's see. She's going to plop. Plop. Okay. So let's get into physics for today. Oh, hey, Sofa. Thanks for joining. So the first thing I wanted to talk about is the solar constant, S. So we talked about the solar constant in the context of solar panels. You might recall that the power output of a solar panel is the efficiency times the solar constant times the area of the solar panel. So that's in this week's quiz, I believe. So how do we calculate the solar constant? So there's a nice formula for solar constant, and it's P over 4 pi r squared. Okay? Where P is the power output of the star. Okay? So that would be the total power output of the sun, which is, as you can imagine, quite large. I believe it's like 10 to the 36 watts or something. Let me look it up. Yeah, 3.8 times 10 to the 26 watts is the power output of the sun. So it's a huge amount of power. But the sun is very far away from us. So R is the distance from the star. Okay? So yeah. So the farther you are away, see how R is on the denominator, the less power that, or the smaller the solar constant is. It's important to know this 1 over R squared factor. So what that means is that, for example, if we moved to half the distance to the sun, then we would square that 1/2. It would be like 1 over 1/2 squared. We get 4 times the solar constant. Okay? So the solar constant on Earth at our current distance is, the solar constant at our current distance is about 1,000 watts per meter squared. Okay? If we were to move to half the distance to the sun, it would be 4,000 watts per meter squared, which would be significantly more. If we were to go to double the distance to the sun, if we square the double, then we would get 1/4 the solar constant. So a planet that is twice as far away is going to actually only get 1/4 the energy from the sun as us. So what's interesting about that is that based on the power output of the star, there's a certain range of distances where the solar constant has an acceptable value for there to be liquid water on the planet. So this defines what's sort of called the green zone. So that you can hear about conversations about green zone around a planet. The green zone is the range of distances away from a star where a planet can be and have liquid water on its surface. And it's a range of values. It's a range of distances because planets can have different atmospheric compositions that sort of change how much heat they retain from the sun. Some planets can be really reflective, so they reflect most of the light. Planets that are reflective would have to be closer to the star in order to absorb enough energy. So this is one of the things when we find planets around other star systems and we want to know, could there be life as we know it on that planet, which would be carbon-based life that needs water and so on. We can sort of look at the distance of the star, or of the planet from the star, and see if it's in the green belt for that star. If the power output of the star is larger, then the green belt moves farther away. Because if you receive too much energy from the star, then all the water is going to just boil. If you receive too little energy from the star, it's all going to be ice. So you got to be the right distance away in order to get the proper amount of energy. So that's the first concept that I wanted to talk about today. So I'll put a dot there. The second concept I wanted to talk about today, hey Michael, is something called albedo, which is denoted by alpha. Okay? And albedo is the fraction of light that is reflected. Okay? So what would be the albedo of a perfect black body? Perfect black bodies absorb all electromagnetic radiation that's incoming on it. So a black body would have an albedo of 0. Okay? All right. If a perfect mirror, a mirror would have an albedo of 1. It reflects everything. So it's the fraction of light that's reflected. 1 minus alpha would be the fraction of light absorbed. right? Because the light is either reflected or absorbed. It can't do both. So it's just the remainder is. So basically, if you reflect 30% of the light, then you absorb 70% of the light. Okay? Now, one of the things that is interesting is that different surfaces have different albedos. So, for example, snow has an albedo that is very large. It's very close to 1. Okay? Snow is a really good mirror it's really good at reflecting sunlight. Okay? Something like asphalt has a very low albedo. Asphalt absorbs light. So sometimes you'll hear people talking about cities having actually a warmer temperature than the surrounding areas, and one of the reasons is that cities have a lot of asphalt that doesn't reflect light. So the city, so whereas nature might be reflecting the light that's coming in, which keeps it cool because it's not absorbing heat. A city is absorbing it and it gets hotter. Another thing about cities is there's a lot of engines running, which produces exhaust heat. And then also cities have less plants. Plants are able to have evaporative cooling of cities. So what we put in cities kind of can determine the albedo of the city and determine its temperature. Clouds have a high albedo. They reflect a lot of light. That's why clouds are white, or they're reflecting all different wavelengths of light. Okay, so the next thing I want to talk about is how can we calculate the power that goes into an object. Okay? So we shine a flashlight on something. How can we calculate how much power is going in? Okay? And so here's the formula. Power in is 1 minus alpha. Okay? Remember, 1 minus alpha is the fraction of light absorbed. Okay? 1 minus alpha times the solar constant times the cross-sectional area of the object. All right? So one of the things about power, if you shined a flashlight at my hand, if I put my other hand behind it, my hands aren't absorbing any more energy because I haven't increased the cross-sectional area. But if I put my hands side by side like this, they're presenting a bigger target for the light to hit, so I'm going to absorb more energy. So for example, what is the cross-sectional area of a sphere? Well, if we think about a sphere and the light is coming in to hit the sphere, the cross-sectional area is going to be pi r squared. Okay? So the cross-sectional area is different from the surface area. What if we had a cube like this? Okay? Wow, that's a horrible cube. Sorry about that. And the light is coming in. What's the cross-sectional area of a cube? It would just be the area of this face right here, whatever face is pointed towards the object. So it would just be L squared. You know what I'm saying? So the let's say that the camera is shining light. Okay, so Jackson asked the question, why is it the cross-sectional area and not surface area? Very good question. So imagine the camera is shining light and I'm trying to capture it. If I turn my hand sideways, then the light is going to go over this side and over this side. And so my hand isn't capturing very much light from the camera, right? If I want it to capture more light, I would have to turn my hand this way to make the biggest possible target, okay? So basically it has to do with how many photons are going to get captured, okay? So I hope that explains it. All right. So this is the formula. So let's go ahead and put it all together. So it's time to put it all together. You might recall that yesterday we learned that the equilibrium temperature is the power that goes in divided by epsilon sigma A, where A is the surface area, to the 1/4 power. Now, we know what the formula for power in is. Power in is 1 minus alpha, okay, times the solar constant, times the cross-sectional area, divided by epsilon sigma surface area. So you can see that the equilibrium temperature depends on the ratio of cross-sectional area to surface area. Okay? So that's kind of cool. So this is our big equation for today. So let's go ahead and do an example. Assuming Earth is a perfect black body, what is its equilibrium temperature? Okay. So first thing I need to know is, what is the albedo of Earth? Okay. Let me look it up because I can't remember what it is. I think it's about, I want to say it's 30% albedo of Earth. Yeah, 35%. Okay. So the albedo of Earth is 0.3. So it reflects 30% of the light that hits it. It absorbs 70%. What is the cross-sectional area of the Earth? Well, that would be pi r squared. What's the surface area? The surface area of a sphere is 4 pi r squared. So we can see that the ratio between those two is 1/4. Okay? If we're assuming it's a perfect black body, the emissivity is 1. So let's go ahead and do this calculation. Let's calculate what is the equilibrium temperature. We would get 1 minus 0.3 would be 0.7. The solar constant I said was about 1,000. That's the solar constant at the surface of the Earth, but in outer space, the solar constant is 1,400. So we're going to use the solar constant of 1,400. Remember, I was mentioning that the atmosphere absorbs some of the light that's on its way down to the surface. okay, divided by 1 times sigma, which is the easiest constant to remember, 5.67 times 10 to the negative 8, times sectional area divided by surface area, which is 1/4. So I got to do that to the 1/4 power. Let me grab my calculator. Let's see. 7 times 1500. And we get and we get 256 Kelvin. What you'll notice is that this is less than 273 Kelvin. So basically, according to our calculation, if the Earth was a perfect black body, the temperature of the Earth would be less than the freezing temperature of water. So all the water would be frozen, and we would have a snowball Earth. Okay? So that's kind of important. So what that means is that the Earth is not a perfect black body. It has an emissivity that is less than 1. Look at the smaller the emissivity gets, the higher the equilibrium temperature. It's on the denominator here. Okay? So what causes the Earth to have an emissivity that is less than 1? The thing is the atmosphere. Okay? So that leads me to the concept of the greenhouse effect. Okay. Okay. And so basically what's happening is, here's the Earth. The Earth is receiving energy from the sun. Okay. This energy, this light that we get from the sun, is mostly visible light. Okay? And visible light is able to pass through the atmosphere. Okay? So visible light passes through the atmosphere and gets to the surface, which heats up the Earth. And as we know, anything that has a non-zero temperature is emitting its own light. So the light from the Earth is emitting its own electromagnetic radiation out, like this. But here's the thing. Some of the light that comes out of the Earth is blocked by the atmosphere. Okay? Why is that? How come the light that goes in is allowed to pass through the atmosphere, but the light that goes out, some of it gets blocked? The reason is the Earth is cooler than the sun. So the sun is so hot that it's emitting visible light, but the Earth is so cool that it actually emits infrared light. Okay? And the atmosphere allows visible light to pass through it, but it blocks a portion of the infrared light that the Earth emits back out. So it basically, the atmosphere acts like a blanket, which heats up which makes the Earth warmer than it would be if it were a perfect black body. Okay? Now, there's a thing called the enhanced greenhouse effect. So having a greenhouse effect is good. Okay? Because otherwise life wouldn't exist. We would all be icicles. The enhanced greenhouse effect is basically we're emitting more greenhouse gases into the atmosphere, which is basically making the atmospheric blanket more effective at blocking infrared, which results in an even lower emissivity, which raises the temperature. Okay? So a little bit of greenhouse effect is good. A large amount of greenhouse effect is bad. We are contributing to the greenhouse effect and causing too much greenhouse effect, essentially. The other thing I wanted to talk about in climate change is something called positive feedback. Okay? So what would happen if the temperature of the Earth goes up? Okay? What would that do to the amount of snow cover on the Earth? Higher temperatures means less snow. So that means that there's going to be less snow. All right? And if there's less snow, remember how I said that snow is very reflective. So less snow means that there's going to be less albedo. And if the albedo is less, the Earth is absorbing more of the sun's rays, which means that it's going to get hotter, which is going to cause even less snow, which is going to cause an even less albedo, which is going to make it get hotter, which is going to cause less snow and less albedo. And it just goes around and around and around. And the temperature goes up and it gets out of control. Okay? So that's positive feedback. It could go the other way, where we could have the temperature goes down, which causes more snow, which causes more albedo, which makes it get colder. So actually, positive feedback is a dangerous thing. Basically, the climate of the Earth is, at least in the long term, is somewhat precarious. If it gets out of balance, if you start having more energy going in than is going out, the problem is we don't notice it in a human lifetime because it happens very slowly. But the temperature of the Earth has been quite a bit different throughout the Earth's history. There's been times where this positive feedback cycle has gone out of control and the temperature's gotten really hot. This is more what was happening in the time of the dinosaurs. Okay? And then there were times when the positive feedback loop went the other direction and we had basically a snowball Earth. And so there are various ways to break out of the cycle. For example, to break out of the cycle if the temperature gets too hot. The temperature gets hot and a lot of plants grow, which sequesters carbon dioxide from the atmosphere and brings the temperature down. If the temperature gets too cold, then you have basically snow covering the entire Earth. So how can we reduce the albedo of the Earth and make it warm up? One of the things that's changed it is volcanism. So volcanoes explode and then the soot lands on the snow, which makes the snow black, and the sun and the Earth absorbs more light. So, anyways, it's an interesting topic. I'm glad that IB discusses this because this is something I don't talk about in my other classes. Anyways, I hope you found that interesting. I will see you next week. Remember, we're taking tomorrow off. And I hope you guys have a really nice afternoon. Sorry the lesson was a little bit long. Bye.